that is inspiring also, what I'm hoping I can do today is use your teachers as mentors to inspire you as well. And that's something that's done me very well. So I'm hoping I can inspire you to continue on today in your education and always strive for excellence. And the second thing I'll reiterate again is to think big. I never would have imagined a little boy. I grew up in a rural area on a tobacco farm in Virginia, and here I am today. I get to travel the world. I get to engage with some of the most brilliant scientists in the world. So again, always have that self-confidence. So what I wanted to do today is to talk a little bit about what we have on space science and engineering research and education at Virginia Tech, to give you an idea. Some of you may be even able to inspire to try to attend graduate school at Virginia Tech in this area. One thing I'll say at the beginning is that notice this isn't everything that we have at Virginia Tech. As I'll mention in a few minutes, we're a very large university, and we have a whole broad spectrum of fields that you could possibly be interested in and studying. So I'll try to present that. And my objectives here today are two. The first one is to give a brief overview of Virginia Tech, to give you an idea of what our university is like, what does it offer, what are some of our interests in research and education. And then I'll go in a little bit of detail about the Space Science and Engineering Research Center that I started about 15 years ago, and it's grown into an international caliber space program. And if my host here give me an extra 5 minutes at the end, I work dominantly in space science and engineering research, but another area that's coming up very, very quickly is quantum information science and engineering, and I may take just a few minutes to give you some ideas of what we're doing there that I've been involved in. Now, so let's start at the leadership. When you look at an organization, it's very important to start there. And so this is the leadership that we have at Virginia Tech. Our president, Tim Sands, he's been with us now about 8 or 9 years. He received, I think, all of his degrees, if I'm not mistaken, at University of California, Berkeley. He's a very distinguished engineer, works electrical engineer, electrical and material science engineer. Vice President Dan Swee is relatively new. Diversity and inclusion is very important in any organization. Our Vice President of that is Minna Pratt-Clark. One thing I'll underscore to you, some issue that we have in the United States is having a diverse workforce in science and engineering. Some recent studies have came out over the last year that show that there hasn't been any progress, virtually nothing in 30 years. And we question, well, what have the diversity and inclusion programs in the U.S. been accomplishing? Is basically just to keep everything status quo. Hadn't been able to make much progress, and so that's something I'm particularly interested in trying to address in my career using my skills and abilities, and that's one reason that I'm here, that I know that you have brilliant students and brilliant faculty members. We would love to partner with you for you to come to the U.S. if you would like to and study at our institution and continue to make our workforce more diverse. Some of you who have familiarity with organizations probably realize that there have been numerous studies that show that the more diverse an organization is, the more effective it is at getting things done. We also have a new campus in the Washington, D.C. area. We call it the Innovation Campus. Our Vice President is Dr. Lance Collins. He's one of the most distinguished African-American engineers in the country. He has numerous awards and honors and numerous firsts. I'll just mention two. I forgot this branch of engineering. Anybody in here that is a chemical engineer? Raise your hand. No. Well, Dr. Collins was the first African-American chemical engineer graduate from Princeton University. Most of us know Princeton's a pretty good school. He was the first African-American to receive his BS degree in chemical engineering. And the other first I'll mention and brag on, Dr. Collins, he was the first African American dean of engineering at Cornell University, which is a pretty good school. I graduated from there. So then we have our dean of the College of Engineering, Julie Ross, and we have a new dean of the College of Science, Kevin Pitts. Now, one thing I want to say before I move on, I was very intentional in putting the deans of engineering and science together because science and engineering work together. I trained myself as a student equally in science and engineering because they go together so beautifully. One thing I'll try to emphasize in the talk for you as students is that these days, to be competitive in the workforce, you need to be innovative and an entrepreneur. And we're changing our paradigm now from going just to doing fundamental research into basically doing research that actually impacts society. And so we see that being very, very important now. Anytime that I get money from our federal government, I have to justify why this is important to society. I also have to be able to explain it in a way that anybody in the public can understand. So that's something that you should think about. And linkages between science and engineering, and then also partnerships with industry are critical. So one thing you need to do is, if you can get industry experience, I'll talk a little bit about how we do that at Virginia Tech. That's critical. So you come out well-rounded, you have understanding of the basic science, but you also understand how it's used and what industry or corporate America or whatever corporate anywhere in the world, what they can actually use it for. Okay, this is an overview of Virginia Tech. We have about 37,000 students, 80% undergraduate, 20% graduate, 90 bachelor's degrees. We're the largest research university in the state of Virginia. We can see we have lots of colleges, all the way from a medical school, veterinary school, all types of important fields of study, natural resources, architecture, agriculture, but of course we have engineering and science as well. So this is one thing, even though I'm focusing a bit on space science and engineering, notice that we have great programs that go across the board. Okay, a little slow on this today. Okay, this shows you the geography of where we're located at. We hope some of you can come, both your administrators or students can come and visit us someday. We're in the state of Virginia, close to we are bordering on the Atlantic Ocean. Our main campus is in Blacksburg, Virginia. And the second campus I mentioned that Dr. Collins is the vice president over, it's very close to Washington, D.C. Literally, it's probably no more than about 2 to 3 miles from downtown Washington, D.C., maybe no more than 3 or 4 miles from the White House. So it's very close. So if you look at our campuses, our main campus is Blacksburg. That's where the bulk of our faculty and students are. Our medical school is located in Roanoke, Virginia. It's about a 35-minute drive from Blacksburg. We have a facility out on the coast in Hampton, and there's a NASA facility there, NASA Langley Research Center, and so there are collaborations between an organization, the National Institute of Aerospace, that Virginia Tech is a member of, and the NASA facility. I'll mention a second, wish I had put it for the talk, on the coast, the eastern shore of Virginia, on this little peninsula here, that's a part of Virginia. We actually have a NASA launch facility there as well, NASA Wallops Space Center. So lots of suborbital missions go out of there. They've also had a few of the moon shots over the last few years that have gone out, and the state is trying to develop that. into a more prominent spaceport. So you can see that we have some very substantial infrastructure within the state of Virginia to do space science and engineering. And the last thing I'll talk about, note up at the top, again, this is our innovation campus, again, located within several miles of downtown Washington, D.C. This is an artist rendition. It should open in 2024. It's a billion-dollar campus, and I'll talk a little bit more about it in a few moments. This slide I'll go over very quickly, but this shows what research interest Virginia Tech has, or what are the most prominent research interests the university is investing in. Again, some of you who may have interest in going to graduate school can note this. And again, we have these four that we're particularly over the last year or two, we've been investing lots of money into. If you look at most big research universities in the U.S., but probably other countries as well, these are pretty common in terms of areas that we think are going to be at the forefront. And so again, those of you who are students now, being able to get into the ground floor in these areas can be very helpful for you in terms of your career. One is artificial intelligence and basically big data analysis. We have a research center in the Washington, D.C. area that deals with that. Health. We have another institute that looks at all types of issues of health. You can imagine that we would have a strength in that because we have actually two medical schools associated with the university as well as a veterinary school, and we have a growing biomedical engineering department. Security, this is an area that Virginia Tech hopes to be number one in the United States in. And again, we like to think big. I like to think big as possible with all the talented faculty that we have. We actually run a statewide cybersecurity initiative that has about 50 institutions, university-type institutions involved. We are geographically located in a very good place near Washington, D.C., and we also have lots of good connections in with the federal government. So we think that we can really be one of the top programs in the country in security. And then the last one I'll mention a tiny bit at the very end, if I have time, is on quantum information science and engineering. This is a field that started to grow very rapidly over the last 5 to 10 years. It's starting to get to critical mass. People are thinking that we could have a commercial quantum computer by the end of this decade, and many think that this is going to revolutionize society. So some of you who may have interest in this, this is another area to look at because there are going to be a plethora of opportunities over the next decade in this area. Won't talk too much about this. These are our big research institutes. These are institutes that typically have hundreds of faculty and research scientists involved, and they pursue specific research agendas. Just note the areas that they're in. Again, these are hot, good areas to go in. If you were to decide to come to Virginia Tech for graduate school, lots of opportunities to work in these areas. We have the Biomedical Research Institute and Biomedical Engineering, Transportation Institute. We're one of the best in the United States there. National Security Institute and the Center for National Security Technology. Again, we're trying to become one of the top in the United States in that area of cybersecurity and such, macromolecules and interdisciplinary for applied math. Then the two on your right, basically these are institutes that aren't based on a specific theme, but they have a group of faculty members working in different areas that basically this is how the university incorporates its seed funding to grow research areas. So they're called investment institutes, faculty members with good ideas, possibilities for building a research program. They can go over and talk to these investment institutes, get seed funding, to start to set up conferences and workshops, to build partnerships with other organizations, so forth and so on, and then they can grow a specific research agenda. The top one, you can imagine, is more life science oriented, and then the bottom one is more engineering and applied science. I think this is my last slide on my intro to Virginia Tech. This is just talking about our new innovation campus. And I wanted to talk about this, and it loops back in with something that I said earlier. As we look at the evolution of research and STEM fields and so forth and so on, a new paradigm is developing. It's not like myself. When I was in your seat, I was interested in how many math equations I could solve, how many physics problems I could solve, how quickly I could do them. And I really didn't think a lot about, well, in terms of the big picture, where is this going to go? How can it really impact the average person's life? Or how can it directly link into what corporate in America is interested in our industry? So that is the whole concept of this new campus that's going up in Alexandria, Virginia. As I said, a couple of miles from the White House and such. It's going to be opening in 2024, and it's a new vision for graduate education. The way that this center came about is that some of you may have heard, how many in here have heard of Amazon before? Everybody, okay? How many people know that Amazon recently started a second headquarters on the East Coast of the United States? They call it Headquarters 2. So this campus came about because Amazon was interested in putting a second headquarters on the East Coast of the United States, and they wanted a university that was good enough to be able to provide educational training for their employees, the ones that they expected to be associated with Headquarters 2. Virginia Tech competed in this competition, and we won. And so basically this campus is going to be built essentially right beside the Amazon Headquarters 2. You know that Amazon has a broad spectrum of interest in engineering and so forth and so on. For instance, our artificial intelligence is one, space science is another. And so this campus is built to serve that type of student that not necessarily wants to be in a position that they want to focus on academic work, publishing, so forth and so on. But these are people who want to be trained to solve real-world problems but need relatively advanced training of a master's or a PhD. So again, this is a unique campus, a unique vision, a new vision of looking at things as a collaboration between academia, government, and industry, project-based learning. So if you get a degree coming out of this program, there's going to be lots of hands-on work where you actually can go in the laboratory, work on projects with groups of students. And this isn't done that often at the graduate level, but that's one of the things that this new campus is going to do. It's pretty aggressive in terms of how many students are going to come out. It's going to be all masters and PhD. These are some of the areas, of course, I mentioned some of these before: cybersecurity, artificial intelligence, wireless next-gen technology, and also quantum information science and technology. We recently got a very large investment to work in the field of quantum, and there'll probably be about a $30 million investment from Virginia Tech to build and develop its quantum information science program. Of course, as I said earlier, we want a very diverse student body, and because this talk focuses to some degree on space science and technology, these are the areas that we want to focus on as far as space science and technology: low Earth orbit, mega constellations. Some of you may have heard of those before, where I have 1,000 or 100 small satellites orbiting the Earth in formation, using that for communications or internet. And then the other is cislunar, the enterprise infrastructure. So probably, definitely in your lifetime, there will be an ecosystem of spacecraft existing all the way from low Earth orbit which is a few hundred miles above the surface of the Earth, all the way out to the moon. So you can imagine people want to do that because we want to eventually send humans into deep space. That's a primary thing that this infrastructure will do. There'll be various space stations out close to the orbit of the moon. The moon actually will be mined for energy to go on spacecraft to send people out deeper into space. And basically this will be a strategy that's going to be used as humans continue to explore the solar system. So these are two of the primary areas that we plan to pursue in our research group in space science and engineering at Virginia Tech, and we've been very fortunate that Dr. Collins has been very supportive of this. Okay, I'm sorry, I got one more slide, I think, in engineering. You know, my wife is here and she tells me I don't tell the truth all the time. So, but anyway, so this is the College of Engineering Demographics, and I know the students will be interested. We are I believe, one of the 5 largest engineering schools in the United States, not in Virginia. We're the largest in Virginia, but we're one of the 5 largest in the whole country, the U.S. We have 13 academic departments, 15 degree programs. We've got over 350 faculty. And again, with the innovation campus, this will probably be over 400 easily it'll be over 400 in 5 years. We have about 11 to 12,000 students, over 2,000 undergraduates. We give out about 1,200 bachelor's degrees every year, and 500 master's and 200 PhD. And so we account for half of the total engineering graduates in the state of Virginia. So again, we're a large engineering school, and for students who want to attend Virginia Tech, I think this is helpful that we have such a broad spectrum of possibilities for you to consider. So that's something that's very important. And again, these show all the branches of engineering that we have, and we have world-class faculty members in each one of these areas. Okay, now, this sort of goes into my second phase of the talk. This is just to give you an idea of what we are doing in space science and engineering research at Virginia Tech. I started this group probably about 15 years ago, just me, yours truly, and we have over 100 people involved in this now. We have a dozen faculty members in electrical and aerospace engineering, so those are the 2 departments we started out, with when we formed the center, or I founded it probably 15 or more years ago. But again, these days we've expanded out to more departments. We have people interested in mechanical engineering, for instance, space robots. So we have a very talented faculty member in that area working in space robotics, and we're looking to hire at least one more over the next 5 years. Industrial and systems engineering, basically space mission design, and of course we have people in physics doing astronomy, and then geoscience as well. So we're growing, continue to grow, and we have a very diverse number of departments involved in this, as we wanted when we founded the center. We've got a dozen research faculty and staff, and we've got 70 or more graduate student researchers. We also probably bring in more undergraduate researchers than graduate students actually, because for instance, during this time of the year, between June and July and August, we bring in a number of undergraduate students to work with us on projects and give undergraduate students a research experience. We have an interdisciplinary undergraduate curriculum, and I'm going to talk about that in a little bit more detail, both undergraduate and graduate. We collaborate with people that do remote sensing. I was a co-founder of the interdisciplinary graduate education program in remote sensing. We have about 12 departments involved in that across 3 or 4 colleges. And then the last thing I'll mention again, well, where does this research group, where do we want to go in the future? Okay, I think this is very important. And again, it's tying back into my theme of we can't really do business as professors or universities when we're doing research as in the past, okay? Again, a change in the seas at this time. So our interest, again, is to work in a direction of being more entrepreneurial, work more with industry. All of our faculty members are like me. We love doing basic research. We love publishing, so forth and so on. We like to go to conferences and speak about our research, write proposals to do more fundamental research. However, to be healthy as we move into the future, we have to be much more linked with industry. So that's one of the key points of what we want to do. You know, all of these faculty members that we have, they're world class in terms of doing fundamental research, but we have to take ourselves somewhat out of our comfort zone to do more industry partner projects. And so an area that we want to work in, and this has linkages to the cislunar orbit ecosystem that I talked about earlier. We want to work in the area of in-space servicing, assembly, and manufacturing. So this is where we see that things are going to go. It turns out, I'll show you, I think it's the next slide, that space science and engineering, at least the area that I work in, is transitioned from a field of more basic science into one of more engineering and industry partnerships, entrepreneurs, so forth and so on. And so that's an important point for people. I want to see if I can drive home. This is a picture to wake everybody up because it's very colorful. It's a very famous picture that was made popular by NASA scientists. And so what I want to do here is to try to explain, if I can, the big picture of the area that I'm working in, both the science and the engineering, and how the two of those fit together. So of course on the left here we have the sun. On the right we have the earth, these little blue lines, or the Earth's magnetic field. So it turns out, and a couple of days ago I got a comment from a student really sharp at another university, and I told him after he asked a question that I want to give him a scholarship because his question was so good. But the point that I tripped him up on, he said that space is a vacuum. Space is not a vacuum. Space is a plasma, okay? So it's a superheated gas of charged particles. I don't think there are any halogen light bulbs in here. How many people seen a halogen light bulb before? Okay, so if you look inside a halogen light bulb, a plasma exists inside, and that's basically how it gives off its light. It's a superheated gas where the neutral particles have been ionized. So this region around the Earth is a plasma. We have disturbances coming out of the sun. It turns out we have a gas flowing out of the sun. That's the sun's upper atmosphere. We can call it, for simplicity here, the solar wind. It typically takes an equiescent state a couple of days to go from the sun to the earth, but you can see here if there is a bad disturbance on that solar activity, and again these beautiful types of structures here, they are actually caused by the sun's magnetic field, okay? And the science of this again is plasma physics. And so what it does, by the time it impacts this system over here, and this is our Earth's atmosphere, it basically can cause all types of disturbances you can imagine. So there's an energy transfer from the solar wind here over to this near-Earth environment around the space. Now, one last thing I'll note here is if you look at the magnetic field, this is actually a shield that's protecting us. So if the Earth didn't have a magnetic field, then we wouldn't be here. We wouldn't exist as a life form. So that magnetic field is so important. But again, all types of disturbances created. I'll show you a computer animation to make it a little bit more clearer in a moment. But what good is all of this? Okay, I've talked a little bit about science, plasma physics, so forth and so on. How does this impact the average person on Earth? Okay, I spent most of my career as a scientist trying to understand, doing theoretical analysis, doing simulations on supercomputers to be able to understand this region around the Earth. But you sitting here or myself on the stage, how does it impact us? That's where the engineering aspect comes in. We know, what do we got orbiting around the Earth? Satellites, okay? GPS, other low Earth orbit satellites. We try to put astronauts, or we do put astronauts in space. Another thing that we actually have down on the surface of the Earth is a power grid. So the disturbances that can happen in this region around the Earth due to all of this energy transfer can impact our modern technologies. We can wipe out GPS signals, these types of disturbances in the near-Earth space environment to the Earth. Also, at the North and South Pole, the biggest signature of space weather, and that's what we call the processes that happen here, or the northern lights, or their southern lights as well. How many people have heard of Aurora Borealis before? Aurora Australis. Basically, when you see those types of signatures, that means that we have lots of geomagnetic activity in this system. Therefore, another example, say if I'm flying on an airplane, a commercial airliner, say I'm going from New York, I'm picking the U.S., I understand it, from New York to Beijing, New York to Shanghai. Basically, if I fly directly over the North Pole, I'm going to receive an extra radiation dose. It may be relatively small, but a stewardess or a pilot that goes on this route often, it may be significant enough to cause a problem. And so what an airline will do, if there's strong geomagnetic activity, they will take a route at a lower latitude. May cost extra fuel, but again, it doesn't provide the radiation dose. So again, this gives you an idea of what we do in our research group. We have all the beautiful physics and chemistry in this very complicated system, but at the end of the day, how does all of this stuff impact us? It impacts our technology. So though that's what we try to do in our research center, we have faculty members that may concentrate more so on the basic science, but we have faculty members that concentrate on the engineering. How do I design a GPS receiver, for instance, so it can take an impact of the disturbances in this region? How do I do satellite communications? How could this impact the power grid? And so I think this field is really a beautiful example of how basic science and engineering can fit together. And that's one of the things, when I was in your seat as a student, that attracted me to the field. Now, let's talk a little bit about how we train students to try to attack this problem. So I'm going to talk a little bit about what we do at the undergraduate level and also the graduate level. So our undergraduate curriculum at this time is based dominantly in electrical and computer engineering and aerospace and ocean engineering. And we actually have a major space systems engineering. So this is typically what you may see at Virginia Tech if you want to work in the space field. We have an introductory course, the 2000 at the top, the 2 at the beginning of the number. That indicates it's a second year, a 3 at the beginning, it's a third year, and a 4 is the fourth year. So we start the students out with an introduction to space exploration, where we teach them about the space environment. We teach them about all the technologies that are used, basics of satellite communications, GPS, so forth and so on, at a very low level, just to get them aware. Then that puts them in the pipeline. They could take, if they're more science-oriented, they could go take a course in astrophysics. However, in engineering, electrical engineering, we have a introduction to space systems and a space systems laboratory. Again, Virginia Tech has a motto, hands-on, minds-on. That means that our students are expected to actually get their hands dirty to work in the laboratory. So what we do here, and you can see the pictures on the right, they basically show students working in this laboratory, and they learn how to do different types of instruments or systems that actually go on a spacecraft, and learn how to use all the types of equipment for electrical testing, mechanical testing, thermal testing, so forth and so on. For instance, this device here, this is a vacuum chamber, and essentially what's done with that, of course, when you're putting some type of device on a spacecraft, it has to work in next to a vacuum, not completely, there's a plasma there, but it can be approximated as a vacuum, and so we, different types of space instruments, we actually test it in this vacuum chamber. Then at the senior year, we have some elective courses you can take. GNSS Theory and Practice, that's a course I typically teach, talks about the theory of how GPS receivers and other GNSS systems work. And of course, it's a project-based course. We have satellite communications, introduction to space weather. This is a little bit more science-oriented. I think most of the other courses are more engineering, remote sensing, spacecraft propulsion, and then spacecraft positioning, navigation and timing, and orbit determination. So this gives you an idea of how we train our students at the undergraduate level. And again, this is a collaboration between electrical and computer engineering and aerospace. And some of you may say, well, how do these two fields link together? I try to explain it like this. Aerospace engineering is really where you look more at the concepts of spacecraft orbits and so forth and so on. And electrical and computer engineering, that has to do with the communication and navigation. I have to have receivers and transmitters, so forth and so on. I have to design signals and so forth. Also, radars are very important in a lot of this work I'll mention earlier. So this is how we set our curriculum up. We also have a ground station. This is just to show more work that's been done by our undergraduate students. So we have a ground station. We can take data down from spacecraft, and so this has been a really good opportunity for undergraduate students to learn possibilities for satellite communications, antennas, radio wave propagation, and so forth. Now, on to graduate students. I'll start with the one at the top left. You recognize the guy in the middle with a smirk on his face. Yours truly, okay? So this is me with some of my PhD students. I do a fair amount of work at a facility in Alaska. I'll mention at the very end of my talk in a tiny bit more detail. So one of the things that we give our students good opportunities to travel around the world and also to do field work. And again, this goes back to the point, we just don't want our students sitting at a desk in a laboratory programming computers and so forth and so on. We actually send them out, and I'll admit we put them in compromising environments, and they are expected to be able to put their engineering practice to work. How do I set up things if I'm doing field work? So for instance, myself here, the work I'm doing in Alaska, all of these students have to go out in Alaska in the middle of nowhere and set up scientific instruments, be able to understand how to take data, and they have to think on their feet, so forth and so on. We also send students to Antarctica. We have a big facility that we developed down there over about 5 or 6 years that measures aspects of space weather. If you remember back in the picture I showed you, the Earth's magnetic field, so that's basically what that facility does in Antarctica. It measures wiggles in the Earth's magnetic field, and then you can detect issues of space weather. We send people to Norway, and then this is a group down at the bottom right. It's a group of our students and faculty. This is led by Dr. Scott Bailey here, and we do suborbital space launches. So again, the students have to travel up there, help NASA get the rocket assembled properly, get the instrument on the rocket, and then take the data down from the spacecraft as it flies in space suborbital rocket typically will stay in space for about 20 minutes, take some scientific data, then come down in the ocean or some remote landmass. Now, this quickly, I think this is the last one on curriculum. This is our graduate curriculum. Again, those of you who may have interest, these are some skill sets that we expect the students to learn. Plasma science, as I said, that's the foundational science for studying a space environment, because space is 99% of plasma, so it's plasma physics. Then we have some courses in space science, electromagnetic waves, remote sensing, radar systems. That's a very popular course because so many, there are a lot of job opportunities doing radar systems, and actually we get lots of students from around the Washington, D.C. area. We teach the course remotely, or you can take it online. We have a lot of students in the area taking radars, GNSS receiver design, orbital mechanics, spacecraft dynamics and control, and then computational plasma physics. So one thing I hope you see here is we try to put in a good mixture of practical engineering along with basic science. Last thing I'll mention here before going on to the last component of my talk is that some people, let's say I go from Ghana to the U.S., I may not have a lot of experience. It's scary. It was scary for me when I transitioned from my undergraduate to graduate institution. What type of programs do you have that transition me into a new type of environment? And we have one of the top people in the country at Virginia Tech, Dr. Trey Waller. So those of you who may have some interest in attending Virginia Tech, he's probably the first name or the first person you would engage with. He's outstanding. He worked at Cornell University before he came to Virginia Tech, and he's designed all of this suite of programs that actually allow students to transition into graduate school, help them get funding, and so forth and so on. We have the Center for Engineering Diversity, Academic and Social Support, New Horizons Graduate Scholars Program. This is a program where we give our top candidates coming into graduate school, they basically get a fellowship, and we put them in a community, a cohort, where they work together. Learning, for instance, as a graduate student, you have to publish papers. Some people may not have done that before, so you work within a group of students. You learn how to write papers. You learn how to go through all the graduate exams, so forth and so on, and also it's social as well, okay? So you get to interact with a broad spectrum of diverse students. Master Your Future, that's basically a set of lectures. I think I've actually given one or two, and you basically give students, you get a motivational talk, step to the doctorate. Basically, it's a bridge program to the master's and PhD for undergrad students. We have various student organizations, and then so forth and so on. So we do have a very robust infrastructure to transition students into graduate school at Virginia Tech. And we're very fortunate to have Dr. Waller, since he has done an outstanding job of creating a lot of that. Now, last part of my talk, and I'll be done. What I wanted to do, those of you who may have a bit more interest in space science and engineering, I'm going to just show you some of the key research agendas that we have in our space research program. The first is the so-called Super Dawn Space Weather Radar. So you may be familiar with when you get up in the morning and you may look at the news and you see a weather map, okay? Talks about rain and other types of weather patterns. It turns out that that complicated system I showed you earlier, you can do something very similar with it and come up with a concept of describing space weather. Of course, the space weather is in terms of electric and magnetic fields and charged particles, but you can do that, and so the people who developed that concept back in the 1980s are faculty members at Virginia Tech. We have another group that looks at the ionosphere and magnetospheric science as a dominantly science group. We have space-based aeronomy and remote sensing. We have modeling and simulation. That's an area that I have worked dominantly in for most of my career. As I said, developing very complicated computer simulations to look at the disturbances in the space environment, very computationally intense. I've used supercomputers for most of my career and basically learning how to program on supercomputers. We have another group that basically does laboratory measurements, builds instruments that actually go on spacecraft. I'll show you an example of an instrument that was built by students, graduate students, that actually go on a space mission. And then the last one is global navigation, satellite systems, and space systems control. Now, I'll cycle through each one of these quickly to give you an idea. This is basically our what we do in the area of space weather radar. Thing to note, the two figures that I have here, the one at the top, you can see these little fans. Basically, they are radar sighted at different points on the Earth. For instance, we're in Blacksburg right here, and then we have a radar, and then it can scan, okay, what the space weather is over a region of the United States. Very similar to what you see on the weather map as a student. And there are different latitudes. These are the newest ones built at mid-latitudes. And again, this is just showing the northern hemisphere. And then you can see the fans go up to high latitudes as well, looking at the polar region, the so-called subaurora region, and also the mid-latitudes. This is what one of the radars looks like. Okay, it's in terms of real size, that's probably about 5 or 6 acres of land. That's what it takes to build one of these on. And again, when you look at this, our graduate students, or some undergraduate students as well, with the help of some of our research scientists, build all of this, okay? They basically build the antenna structure right here. And also, you see there's a little house here. All of the radar electronics exist in there. So our students are involved in doing the radar electronics, putting the antennas up, but also we have another group of students who may not want to do pure engineering. They actually take the data and they do a scientific analysis. So again, science and engineering working together, okay? And we give our students an option of going in either direction. We probably put just as many students working at Netflix and Apple and Google after they graduate as we do being professors at universities. So again, you know, if you get a PhD, you don't have to necessarily end up as a professor. You know, you can get a very well-paying job. And of course, most of my students, some of them actually work on Wall Street in New York, and they make much more money than I do. At least they feel guilty about it. That makes me feel a little bit better. We make so much more than you, Professor Scales. We're guilty, but again, they keep making their big salaries. So that's our space weather radar. One thing I wanted to mention that is a new development here is that we're actually building one of these radar systems only about 200 miles from here in Nigeria. So this is going to be put up at Bowen University, Iwo, Nigeria, and this is the first space weather radar in sub-Saharan Africa, maybe the only, I think probably the only one on the continent of Africa. So we cut this deal about 2 years ago, and just to show you some science and engineering working together, let's look at a GPS system up here, and this is a classic figure. Actually, it was created by my PhD dissertation advisor about 20 years ago. But you can see that you have a GPS satellite, the so-called ionosphere. That's a layer of plasma in that figure that I showed you earlier that exists between 100 and 1,000 kilometers above the surface of the Earth. And so let's think about your GPS on your cell phone. How does it work, or how is it impacted? There are two ways. One is that the signal goes from your GPS satellite down to your GPS receiver. And this figure is shown as an airplane. It could be your cell phone, so forth and so on. Now, one thing that this layer of this plasma does is it actually slows the signal down. Some of you who are electrical engineers or taking some physics and know about radio propagation know that when you increase the index of refraction, a signal slows down. And so that's what the ionosphere does. It slows the signal down. Turns out that your GPS receiver considers the the radio wave moving at the speed of light, all the way from the satellite down to your GPS receiver. It slows down in the ionosphere, and then therefore your GPS receiver miscalculates the transit time if there's a large increase in the density in the ionosphere. So that's the biggest cause of error in GPS. The other way, if I have lots of disturbances there, like are shown on the right, there's all types of scattering in that region. Destructive interference, again, those of you who know a little bit of wave mechanics understand that, and basically you can get fluctuations in the amplitude of the signal by the time it gets to the GPS receiver. This is called scintillations. If the signal is so weakened by that constructive and destructive interference, then your GPS receiver can't track the satellite anymore, and you lose your ability to navigate. Okay? So that shows you some science and practical engineering fitting together. One big engineering problem, for instance, is can I design a GPS receiver to mitigate the best as I can the drop in the signal strength due to these types of scintillations. Again, one thing we can do here, we can actually scan the region where these so-called ionospheric irregularities are, pick up where they are. That may give us some prediction of how well the GPS is going to behave in that region. So again, we're using the basic science, space weather, and then we're applying it to a practical engineering problem. So we wanted to put one of these facilities up in sub-Saharan Africa. Why? Turns out that we're at a very interesting latitude. I don't know, some of you may know, what's your latitude here, like 3, 4, 5 degrees off the equator, something like that. Turns out that the magnetic field in this geographic region is horizontal to the surface of the Earth, and that means that those disturbances are very, very violent in sub-Saharan Africa. This is just a visual. I won't go into detail, but that's how we plan to make the measurement at this facility in Bowen University. And again, this is the site. This was a couple of months ago showing that the site has been cleared. We're actually at the point where we're getting ready to put all of the antenna poles up. We've built the building to put the radar electronics in, and we were very fortunate a few months ago. The United States Air Force is very interested in this project, and again, it has to do with this figure here. If you look at military systems are negatively impacted by space weather, turns out in sub-Saharan Africa, this space weather is very violent, and so they're interested in how this can impact or negatively impact their military navigation and communication systems. They were trying to build a facility in the South Pacific, so that the deal fell through, and we said, hey, we're trying to build this in Nigeria, and so basically they're donating us all of the electronics. I fell out of my seat when I got the phone call that they were going to do that, and so the U.S. Air Force will be providing the radar electronics. So again, this is a very exciting development. The scientific community is very excited about this because it hasn't been done before, and we hope to have this facility done within about a year. And again, last thing I'll say, this is an advertisement, unashamed, that what the big vision would be to put 3 or 4 of these antennas across sub-Saharan Africa, so we get a swath of a space weather measurement. At this time, that does not exist. That's one of the things why this is important, is because there's a dearth of this type of data over Africa. So we can put one here, maybe one over here in Ghana. We'll see. Okay, so that's an unashamed advertisement there. Okay. Now, I try to finish up in about 5 or 10 minutes or so. This is just showing our magnetospheric ionospheric team. That's the South Pole. You see the little green dots on there. Those are where these types of stations are being put up. These actually measure fluctuations in the geomagnetic field by an instrument called a magnetometer. And again, that gives us another way of looking at space weather other than using the space weather radar. We also have GPS receivers into each one of these stations to look at how the GPS signal is impacted. And again, students, experiential learning, field work. These are students. We fly them down to, when we're building a facility, fly them down to Antarctica. They would stay about 40 days and basically build one or two of these facilities. That's why it took a number of years, because we only have a window of 40 days, typically between late November and mid-January. They would come down, get as far as they could when the weather was favorable, and send them down every year. And so they finally finished this. So a lot of groundbreaking work has been done here. This is a group that actually builds instruments that go into space. Notice that the two previous examples I showed, these were so-called ground-based measurements. Okay, I have a radar on the ground. I look up into space. I make a measurement. Or I have a magnetometer or a GPS receiver on the ground. I look at the impact of the signal as it goes through the ionosphere. These two groups here, this one and the next, I believe, actually build instruments. This just shows an optical instrument that goes on a spacecraft. This is one of our launches here at Virginia Tech, and that instrument was built over the probably period of maybe a year or two. And then again, we send the faculty and the students out. NASA puts the payload on top of the rocket and launches it. It's in space for 20 minutes, and then we actually make scientific measurements. This is the work that I do, which is plasma modeling and simulation. I'll just show you. This is a simulation one of my last PhD students did. So you probably remember that figure I showed you earlier. That's the Earth. We have the magnetic field around the Earth shielding us from the solar wind and the plasma. All I want to do here is just to show you how violent and turbulent this region is. It works. Okay, and so again, the sun is over here. The solar wind is coming towards the Earth, and you can see some of the magnetic field contours. And then this is real time. You can see we're in the simulation, and you can see all of that structure. It'll get more violent in just a moment. And you can see all of the turbulence. There was a big gust of the solar wind, and you can see all of that interesting dynamics. And again, that's a very complicated fundamental physics problem, but again, you can imagine if I have a spacecraft out there, or I have an astronaut that's trying to do an extra vehicle activity, that the astronaut could be hurt, a spacecraft could be wiped out, so forth and so on. Again, it impacts GPS and communication signals and so forth. That's why it's important for us to understand fundamentals of how this system works, and then go the next step further, how this impacts our technology. Two more of these left. This is our group that actually builds instruments to go into space to make measurements, again, so-called in situ measurements. This is a very important field here, especially in the U.S. How many here have heard of the term CubeSat before? Okay, good. So basically what this group has spent quite a bit of its time doing is building instruments to go on CubeSats. Those of you who don't know, they're spacecraft about the size of a shoebox or a loaf of bread. This is the future in space technology. The price of one of these is probably, let's say, on average about $1 million US, at least in the US. A full-size spacecraft, say the size of a car, it may be $500 million. So you can see what's going on here is that as technology evolves, we can make spacecraft smaller and smaller. You can imagine that we could send 100 of these up to do some type of complicated mission. And so this is an example. This is an artist rendition of a spacecraft that we built at Virginia Tech. This shows the frame of a CubeSat over here. And again, this was built and developed by students. And that's the instrument up at the top that will be mounted on the instrument, and it'll do a specific type of science mission. I won't go into the details of the science. But if we look at a number of countries, the U.S., for instance, this is what we see the future in terms of training students in space science and engineering. What we would like to do, say when a student comes in at their first or second year, you start to go through a curriculum, just as the one that we've shown you, and then you start to develop all of those tools that would allow you to build a CubeSat. And then by the time you finish up your fourth year at university, you're actually able to build a working CubeSat that could actually be gone into space and do a specific type of mission. Somewhat it could be a science mission like this one, or it could be something more engineering or engineering technology focused as well. So this is what the future. I serve on a trustee board of NASA's sister organization, which is called the University Space Research Association, and I was involved in presenting these types of concepts to the U.S. Congress, and then trying to get the U.S. Congress to put in about $50 million into U.S. universities so we could set up a program like that in which we would put the infrastructure in so our students could be in a position by the time they finished up their undergraduates, ones who were interested in space science and technology, they could have the experience where they could actually build a CubeSat. Last one, I think, here, next to the last one. This is just showing some of the research efforts I have in global navigation satellite systems. Basically, I work also in the area of GPS and understanding the impact of the space weather on GPS. The one at the top right, this shows some simulation done by one of my former PhD students. You see all the interesting structures. That's just an example of the type of turbulence that develops in the space environment due to space weather. And again, we're taking this information and trying to see how it impacts navigation and communication systems. This is basically turbulence or structures that are developed naturally. You may have a point where, can I develop space weather, or can it be artificial? Can I produce space weather? Is there man-made space weather? And we do that at this facility. I said I'm in Africa. I am in Africa. But Alaska, that's where I was when we did this work. And so this is an antenna array. It's the most powerful high-frequency transmitter in the world. It's called HAARP, the High Frequency Active Auroral Research Program. And we send up lots of power, and in terms of radio waves here, it actually hits the space environment and creates its own turbulence. Therefore, we can control how we produce turbulence, and then look at that controlled turbulence that we produce, how it can impact GPS and communication signals. Last two down here at the bottom, this is one of my laboratories that we use to study techniques as far as space missions in terms of designing formations of spacecraft flying together, what types of space weather measurements we can make. This type of laboratory is called a hardware in the loop formation flying test bed. This was developed by my graduate students over the period of 3 or 4 years. It turns out that NASA actually pioneered this back in the early 2000s. I went and visited NASA and got a tour of this, and I said, how much will it cost me? They said $50 million. And you can imagine I walked out of the room at that time. And so what we're able to do, probably 15 years later, you can imagine that the cost of technology comes down. So we were able to build this system, which is much more sophisticated than the original NASA laboratory. NASA uses it for all of their big space missions in terms of satellites flying in formations. We're able to reproduce this for about $2 million. And so we've got some good attention out of that. Actually, we have companies looking at us trying to commercialize some of the software that came out of this. And this is just the last one. Again, this is a large-scale simulation of space weather that we can use to design missions along with the laboratory on the left. So that's all I have to say. So thank you for giving me your time, and I'm happy to answer any questions you may have.
We know the effects of using computers to the environment. Is there a way that you are mitigating these effects through green technology or something? Yeah.
We can go back and talk about GPS. Some of these effects actually can't be remediated by new technology. Some can, some can't. Okay, so let me try to do two pieces of that, two examples. Okay, the first example, let's say that there's a big solar storm like this. We go back to my figure. Wrong direction. So let's say that we have a big solar storm and it's coming towards the Earth. What the objective in this field is to develop these big computer models so we can predict when that happens, right? Okay, so when you look at weather in the lower atmosphere, you know, you can predict a couple of days in advance if it's going to rain, right? So what we would like to be able to do is predict what the environment is going to be around the Earth. So that's the end game. That's the big picture of what we're trying to do. Currently, we don't have computers that are big enough to be able to solve that problem, because this is quite a bit more complicated than weather in the lower atmosphere. So let's say that I look at the problem. If I'm doing a computer simulation, I have to simulate all the stuff coming out of the sun and what all of this stuff is going on around the Earth. It turns out, in terms of spatial and temporal scales, that's about 10 orders of magnitude. And so no computer that I know of now can solve a turbulence problem like this that can solve 10 orders of magnitude. You're lucky if you've got a computers now big enough to do 5 or 6. And so that's the bottleneck, is that you have spatial scales, you know, they could be comparable to the sun, and then some of the structures down here close to the Earth that can impact the navigation or communication system, they may be down on the scale size of a centimeter. So I'm going for something that may be on the scale size of partially or an order of magnitude less than the sun, the centimeters. You can't do that on a computer, okay? There are some ways that you can get around it. So what I would tend to do, or what people tend to do, is if it's a spacecraft, they don't, the only thing I can do is move its orbit. Okay, so that's typically what people do. It's just like if you have a nice car and you've got your windows open, you don't leave it outside in the rain, you can drive it into your garage. I move the location of it to remediate the impact of the weather. Okay, so that's one way. A way that actually you can see how technology comes in is with the GPS. Okay, I missed the slide. So basically, notice that this is the signal strength of a GPS receiver on the ground. When all of those effects are there, you see this fluctuation. These little flat regions here mean that the GPS signal, and again it could be a GPS signal in your cell phone, has gotten so small that the GPS receiver can't track this GPS satellite anymore. So the question is how could I design the signal processing? And again, this is an electrical engineering problem. How could I design the signal processing inside the GPS receiver to be able to pick up this very weak signal? And so that's how you would do that, okay? There's a whole area of research called weak signal GPS, and that's what people do, use all types of fancy signal processing to be able to pick up a much weaker signal. A lot of the techniques actually come from radar technology. So actually I teach a class on that, so at least I did in the past. So hopefully that answers your question. Okay, any other questions? Okay. Yes.
My question is on GPS
Yeah.
still. So I work with a lot of low-powered electronics, so like 3v3 voltage level microcontrollers. And one big problem we face here especially is that sometimes you design, electronics to meet a certain form factor, and when you're in like a building or in the workshop, you don't get any signal at all.
Yeah.
So you need like really oversized antennas for it to work in such
Yeah.
environment. So I just wanted to know what direction, because I know low-powered electronics is also becoming a big thing now.
Yeah.
And what direction, let's say, GPS research is going now.
Okay,
in
good.
order to.
Yeah, good. That's an excellent question. Basically, there are a few companies now in which they are working in this area of weak signal GPS. It's a very tough problem. I actually worked with one of these companies in Boulder, Colorado on a problem pretty much like you were talking about. We were trying to look at what signal strength we could get inside of a building. And so as I think I sort of answered the question to in as much detail as I can without talking offline, is that that's what people are doing. If we look at radars have to pick up a very weak signal. Okay, so let's think of how radar works. I look at my signal from my transmitter, it hits something, and then it reflects back. So you actually end up with a very weak signal. Those of you who know a little bit about radio wave propagation, the amplitude of a radar signal reduces as what? The distance to the 1 over the distance to the 4th power. So it's a very, very weak signal. And so the techniques that people have been using in radar signal processing for decades to understand or pick up a weak signal from a radar, they are now utilizing those in GPS. And so that's basically the strategy. So that's the direction that the research is going, typically in a weak signal GPS. I'm happy to provide you with some publications or some references if you're interested. So thank you. That was a very good question. Any more? Yes. I'm sorry? You want me to tell you the story? I'm happy to do so, okay? It wasn't intentional, okay? Wasn't intentional. So how this happened in terms of doing the facility in Nigeria, one of my students, was working, I showed you the big computational simulation model there, and he was working at the National Center for Atmospheric Research in Boulder, Colorado. So in the U.S., that's where most of the big weather models are developed and run, okay? You know, to predict hurricanes and tornadoes and so forth and so on. So that's our key weather model development place in the U.S., National Center for Atmospheric Research. So he was doing an internship there doing his PhD. I was invited out there to talk with some of the scientists, and it turns out that they have a very nice internship program there. And one of the interns was a young woman from Nigeria. And so, you know, I walk up, and, you know, I have to be blunt. So, you know, I'm always looking for opportunities. And so I started talking with her, and I got kind of interested in what she was doing. And then she said, well, you need to talk with my PhD dissertation advisor in Nigeria. I contacted him. Then we had a very good discussion, and I was thinking, always thinking in the back of my mind, opportunities. You know, what could we do together? And I said, hey, MIT, Massachusetts Institute of Technology, had tried to do something similar in Ethiopia in terms of one of these radars, but they had failed because the technology that they were using was too, in my opinion, was too expensive. And I said, you guys are located at a great position on the equator, which a lot of breakthrough science can be done at. And also, you know, there's a lot of interest in how the space weather impacts GPS and communication systems at the equator. So I just put the idea on the table. What about if you guys, you know, would allow us to build one of these radars? And then that's how it all started. And then, again, things moved along very well. I made a trip to Nigeria about 3 years ago. I met with the vice chancellor of several universities. I met with a CEO of a communication system company, and also went to Abuja, and I met the head of the Nigerian Space Agency, and I tried to do my best to be a salesperson. Everybody bought in. And so that's how, you know, we got resources from Virginia Tech. We got resources from Bowen University. They are probably the dominant source in terms of doing all the construction, putting the buildings up. And the Nigerian Space Agency, they provided the engineering management and also paid for shipment, for equipment to be shipped from the U.S. And then the last component that just came in is that the U.S. Air Force, they provided all of the radar electronics. And so that's how everything came together. So if I had met a nice Nigerian scientist at NCAR, we would have gone in that direction as well. But again, one thing we would be quite interested in discussing, I discussed this a bit. I presented at the Ghana Space Science and Technology Institute yesterday. They had interest in this, and we hope to continue to talk with them. But, you know, we need a space to put it. We're very fortunate in Nigeria that they donated us about, I think it's about 15 acres of land to put this on. And again, we probably need about half that, but they are sort of trying to look into the future. You know, we can expand this in the future. So that's how everything fell into place. So.
Okay, so thank you, Prof. Skills, for this lecture. It was really informative, and I must say some of us learned something new today. We have a package for you for, yeah. you so much. William will present it to you. Thank you, William. Thank you too. Thank you so much. Yeah. And the tech speaker series will be continuing throughout the year, and you should stay tuned for more thought-provoking sessions. Okay? Thank you so much and have a good evening. Bye.
Why do we have problems? But rather, how can we spin those challenges into opportunities? This is the revolutionary mindset we, students here at Academic City, are driven by. Academic City, we believe that the challenges of today are nothing like the opportunities of tomorrow. Hence, we're poised for the future. And so we say,
come join us.
Pakuli.
Biasonyan.
Oyai Tibatane.
Zalfula Nabia.
Viens nous rejoindre.
Brabe Kayan. Ao, Amanasat Shamegojao.
As we lead the charge to empower the next generation of future-ready leaders. Academic City University College, redefining university education. Today, the question is no longer, why do we have problems? But rather, how can we spin those challenges into opportunities? This is the revolutionary mindset we, students here at Academic City, are driven by. Academic City, we believe that the challenges of today are nothing like the opportunities of tomorrow. Hence, we're poised for the future. And so we say,
come join us.
Pakuli.
Biasonyan.
Oyai Tibatane.
Zalfula Nabia.
Viens nous rejoindre.
Brabe Kayan. Ao, Amanasat Shamegojao.
As we lead the charge to empower the next generation of future-ready leaders. Academic City University College, redefining university education. Today, the question is no longer, why do we have problems? But rather, how can we spin those challenges into opportunities? This is the revolutionary mindset we, students here at Academic City, are driven by. Academic City, we believe that the challenges of today are nothing like the opportunities of tomorrow. Hence, we're poised for the future. And so we say,
come join us.
Pakuli.
Biasonyan.
Oyai Tibatane.
Zalfula Nabia.
Viens nous rejoindre.
Brabe Kayan. Ao, Amanasat Shamegojao.
As we lead the charge to empower the next generation of future-ready leaders. Academic City University College, redefining university education. Today, the question is no longer, why do we have problems? But rather, how can we spin those challenges into opportunities? This is the revolutionary mindset we, students here at Academic City, are driven by. Academic City, we believe that the challenges of today are nothing like the opportunities of tomorrow. Hence, we're poised for the future. And so we say,
come join us.
Pakuli.
Biasonyan.
Oyai Tibatane.
Zalfula Nabia.
Viens nous rejoindre.
Brabe Kayan. Ao, Amanasat Shamegojao.
As we lead the charge to empower the next generation of future-ready leaders. Academic City University College, redefining university education. Today, the question is no longer, why do we have problems? But rather, how can we spin those challenges into opportunities? This is the revolutionary mindset we, students here at Academic City, are driven by. Academic City, we believe that the challenges of today are nothing like the opportunities of tomorrow.